Here we go.
Got it.
Okay. Hello. Want a Rice Krispie treat? Sugar is always a danger when they come here. All right, welcome to GAAC again. All right, we got a little bit of a narrative, and there's an announcement I need to make as well. Our speaker for tonight, who's also from our burgeoning New Jersey branch of GAAC. I can't discuss his healthcare specifics, but he sent me a picture of himself on a respirator. So he's not here tonight. That was enough of an explanation for me.
No.
But we had an opening in September still, due to my mismanagement, and he plugged right into that. So that's good. So, but tonight we have Jim Nordhausen, who was here last time, went on a wonderful whale watch with us that weekend, had a great time, who talked, what's that, chapter 2, Jim?
What's that?
Was what we heard from you last time, chapter 2?
3, actually.
Chapter 3. All right, we're going to hear of chapter 3 of astronomy in Antarctica. What? Oh, you were making I'm alarmed motions. Okay. We're going to hear part 1 tonight. And it includes balloon launches and meteorite searches, and maybe both at the same time. That would be fun. Okay. Thank you, Jim, for filling in on very short notice.
No problem, no problem.
The announcement I have to make is due to scheduling conflicts, our September meeting will be online only. All right, we don't have the room. And rather than move it to Labor Day weekend or to within a weekend of our traveling north for our annual trip north, it seemed best not to have a physical location at all. So we're going to have a really good meeting. I'm really looking forward to Cliff talking to us about galaxies, galaxies, galaxies. He's going to talk about his exploration of the local group out to the limits of the Virgo supercluster. So that should be fun, but it'll be online. Okay, if you're not on the listserv, you need to talk to somebody about how to get on the listserv so you get the invitation to the Zoom meeting for September. Okay, so without further ado, I'm going to kill some lights. And Jim, you can share your screen at any time. Okay.
Perfect.
Okay, so are we ready to begin? Okay, so this is another talk about extreme astronomy, but this is where I began. I originally gave this talk in 2016, so it needed a little bit of updating. You may recognize a few of the slides from last month's talk, but it's maybe only 4 or 5. Now, why do we need extreme astronomy? Oops.
Oh, wait a minute, Jim, I clicked on the wrong thing. You got to share again.
That's okay. There we go. So, why do we need extreme astronomy? Same reasons as last month. The Earth's atmosphere sucks. Photons are sucked out of thin air in various wavelengths due to molecular and particulate components in the air. What reaches the ground is mostly in the visible and infrared. So you have the visible wavelengths here. The atmosphere is relatively transparent there, pretty transparent in radio waves, but a lot of the electromagnetic spectrum is completely blocked out by atmospheric components. And as you see here, these are some of the major components that do the damage, and water vapor is by far the worst of them. So what's the answer? You can observe from places where you don't have any water vapor in the air or a minimal amount. So you can go up to space But satellites, you're talking 120 minimum for launch. That's without the rockets. You can't upgrade instruments on a satellite, but there are cheaper alternatives. You can go do balloon astronomy, high deserts of Chile, Hawaii, or Antarctica. It may seem like a bad place to do things, but it's actually quite good because it has the lowest precipitable water vapor content on Earth. So it has half of that at the Atacama Desert in Chile, where they do a lot of this kind of research, and low atmospheric aerosol contents, so you get less light scattering. So up here, it's hard to see in the slide, but you can actually see stars in the sky with this gentleman's thumb just blocking out the sun. Now, a little background, the first astronomical observations were done in Antarctica in 1911 and 12, and they were just transit sightings to determine coordinates for navigation. Now, the first actual astronomical find was a little different. Douglas Mawson's Australian expedition found a nice meteorite there, nice chondrite, and it was the subject of the first scientific paper ever emanating from research in Antarctica. That's a nice sizable chunk there, but not much was done after that. The director of Yerkes was asked if he wanted to investigate doing astronomical work in Antarctica, and he said, "No, keeping time isn't going to be easy there, so let's pass on that." But 80 years later, Yerkes was the headquarters of the Center for Astrophysics Research in Antarctica, a 10-year program that after it ended, Yerkes still contained a lot of control. We did some of the CARA work last month. So our first stop in this expedition is McMurdo on the coastline of Antarctica. Summer, a hustling, bustling population of 1,500 plus people. Winter population, only about 150. It's only maintenance people to keep things running. But it is the gateway to Antarctica. All travel to U.S. research stations begin here. McMurdo, South Pole Station, and up on the end here, they have a Palmer Station, does mostly oceanography research. Now, port of entry for everything that comes into Antarctica. It's the home base of the ski-mounted remote site balloon launch equipment. It all overwinters there. The cosmic ray measurements are done there, or at least they used to be. That was the earliest research done in Antarctica, funded. And also it's the base for ANSMET, the Antarctic Search for Meteorites. So this is a view of McMurdo. It's a hustling, bustling little community here on Ross Island. A little bit of ice sheet connects it to the mainland. And this road that goes up here and out this way goes out to the Pegasus Field, which is the only place wheeled aircraft can land. The big ones coming in with supplies and things like that. Everything else that goes inland has to get transferred to smaller aircraft or to ski-mounted C-130s. Now, the U.S. Navy established permanent bases at McMurdo and the South Pole in 1956 as part of the International Geophysical Year. And that same year in 1956, Martin Pomerantz at a Bartol Institute in Delaware was invited to do cosmic ray research in Antarctica. And he immediately saw a wide range of potential for different kinds of research there. We discussed him last month in great detail. So he installed cosmic ray detectors in McMurdo in 1960 and at the South Pole in 1964. And that marked the beginning of high energy astronomy in Antarctica. Now, most of the cosmic rays detected are originating from the sun. And in fact, in late 1960, shortly after the COSRAY McMurdo detectors were installed, he was on the way to visit them. And that detector and one in Greenland simultaneously detected a solar flare. So that was the first simultaneous detection and from both poles. But cosmic rays aren't detected directly. They're destroyed as they enter the atmosphere. This triggers what is called a cascade event, which emits other particles, protons, neutrons, and other transient particles. And neutrons are what the cosmic ray detectors actually detect. And high latitude sites for detectors are essential as the Earth's magnetosphere deflects charged particles, severely compromising data at mid-latitudes. Everything sort of gets funneled to the poles, like, that's why aurora formed there as well. So there was a mural inside the CosRay building, which kind of depicts a cascade event. Here's a cosmic ray coming into the atmosphere, and as it gets destroyed, you got neutrons coming off here, protons coming off here. I'm not sure what's coming off down here. It's a pi muon, I think, and they're going into pair production. And over here, you've got some other particles coming off and electrons, and it's a whole slew of particles from the destruction of the cosmic rays, but it's the neutrons that are actually getting detected. So the original CosRay building was built in downtown McMurdo, made sense at the time, but in 1962, the Navy was field testing this portable nuclear power plant designed for extreme environments. They figure, it's a nice mainland place, as cold as they could get. What better place for extreme environment testing? So this led to a bit of problems. The neutrons emitted from the reactor were easily detected by the cosmic ray detectors. So they had to build a new building on the opposite side of a big hill so that the landmass would shield their detectors from the neutrons being emitted from the nuclear reactor. So both sites were active for a short while to ensure continuity, but the detectors from the original building were torn out, and those were the detectors that were installed at the South Pole in 1964. So the nuclear reactor was working for 10 years and provided power for the desalination plant. It was shut down in 1972. No incidents were reported. And all that remains is this plaque erected in 2010. So in May 1979, the decommissioning was complete and the site released for unrestricted use. So it mentions a power output of 1,800 kilowatts and also exported steam that was used for the desalination plant. So that was the only nuclear power plant ever operated in Antarctica. So this is McMurdo's second CosRay building, the one that was built on the opposite side of the hill, and that was in continuous operation since 1962. Notice nothing down there is very attractive, and most of the buildings don't have windows even. They're all utilitarian, designed for, good insulation, etc. But inside the building, this is a bit of the part of the detection system. So there's 3 banks of these, and each bank contains 6 of these detector tubes. They're surrounded by polyethylene sleeves, and if you could read on here, they're marked for the Bartow Research Institute, University of Delaware. They're also listed as B26 or 28 Chalk River neutron counter tubes. And I'll get a little bit to the significance of that. So this is what one of those tubes look like. They're filled with boron trifluoride gas. And I had never heard of Chalk River before I started researching these. But the Chalk River nuclear facility was Canada's delving into safe nuclear use for civilian power generation. And they had a severe meltdown in the 1950s. And it was actually Jimmy Carter who came in and saved the day and led the team that helped shut down the reactor and averted total disaster. So these neutron counter tubes were used to monitor the radiation coming out of the nuclear reactors and were named after the facility. But they all sit inside these lead rings in their polyethylene sleeves, and they're also surrounded by a polyethylene sleeve around that used to be paraffin in previous years. but they're to moderate the neutrons to more reasonable detectable levels. And all the detectors around the world in these systems are all designed the exact same way, so that they're all, the readouts are sort of compatible with each other in terms of flux. So this is the actual interior of the building. You have a bank of detectors here in one direction. You have two more banks of detectors here facing 90 degrees to it. Over here, you have an old teletype machine, which is how they used to record the data, and some more modern computers circa 1999 when this photo was taken. And this is the old teletype machine, original, was still in the building until the building was removed. And they didn't throw away anything. They still had the bucket of little paper chips that was punched out of the teletype machine. So at the time I originally wrote this, Bartol was still doing real-time data from McMurdo. This was from 2016. This is like 10 days worth of cosmic ray output. You can see the different flux depending on what's going on the sun's surface. And this was averages over the 6 previous months. And still other detectors like the ones at the South Pole and Greenland and other parts. All the data is accessible through Bartol's website. And COSRAY is still significant today, part of a global cosmic ray detector system called Spaceship Earth. Now, COSRAY in McMurdo's future, well, it had none. They took down one detector bank in 2014-15 and reinstalled it at the Korean base on the other side of the continent. And the 2 other banks were moved in 2016-2017 and installed at the same Korean base. So now they're operating out of there. You can still read the data through Bartol's site. I don't know the fate of the actual COSRAY building, but everything is a fight for power. So I'm not surprised that it moved on if it was no longer relevant there and they needed the space and the electricity for something else. But for more information, this is Bartol's website, and it's a wealth of information. They even have a nice section on how they built one of the newer detectors from the ground up, from groundbreaking to its first cosmic ray detections. So we're going to move from cosmic rays coming down to something else coming down. ANSMET, the Antarctic Search for Meteorites. So this is a program where, let me start at the beginning. After that first meteorite find in 1912, the next meteorites weren't found until, excuse me, 1961 and 1964. There were 3 collected. Then the Japanese expedition found 9 specimens in one season. And they started to realize by where they were finding them that there was a naturally occurring concentration mechanism. So that led to the startup in 1975 of ANSMET by the US Antarctic program to formally go out and collect the meteorites. Now, this is how the meteorites are concentrated. It's hard to see on here, but where my cursor is going down here is actually the glacial surface. So what happens is the meteorites fall, they get gradually buried by snow, and over hundreds of thousands of years even, they get buried in the glaciers. The glaciers flow, and there's a big ring of mountains, the Transantarctic Range, that sort of block the glacier's flow before it gets to the ocean. So the ice has like upwelling as it gets to the mountain range, and due to the katabatic winds coming down, constantly scouring the surface, all the ice gets sublimated off, and it's left with meteorites just sitting on the surface waiting to be picked up. And they can tell whether they're meteorites or stones pretty much by looking at them, looking at surface features, etc. So this blow up here is this little square on the Antarctic continent, and the Transantarctic Range goes across here. This is the mountain range going across. And right on the inland side of it is where all the stranding stones are, where the glaciers come up against the mountains and deposit their there are meteorites there. Now, ANSMET's based in McMurdo. A lot of people, anyone can really apply to it, but it's not a democratic process for selecting candidates. Preference is given to people who've done it before because they have the experience, and preference is given to people who have sort of a reason to be there, kind of, you know, if that work in meteorites or graduate students or research associates or people like that. But yeah, they usually field 1 or 2 parties out in the field, 6 to 12 members per season. Unfortunately, due to COVID, the last 2 seasons, ANSMET has not operated. I think they're planning on another recruiting drive for the next season, however. And basically what they do is they get airlifted on the Twin Otter planes out into the stranding zones with all their equipment. They set up a base camp of tents and they go out in the field on snowmobiles and on carefully laid out transects and go hunting. All of the groups have a mountaineer with them because as Julianne Gross from Rutgers, who's served twice on there, has said, you can come across a crevasse, you fall in and you die. You get stuck over here in bad weather, you die. You know, every other sentence ended with you die. So they have experienced guides going out with all of the teams. And so they spot one. Often they ride the snowmobiles like from a standing position so they get better view. They like sort of go all in a line, all in the same direction. So they see one, they measure it, they catalog it, they give it a number, then it's carefully bagged and tagged, and then it's stored actually on ice until they get back. But they all sleep in tents. They're allowed to have like up to a case of booze per person, I think, or per season. And I forget how the actual rations work. It depends on what you're doing, whether you're doing field work or in the McMurdo or South Pole. But they did try an experiment doing the robotic search method, but they found out while the robots could physically discriminate fairly easily, humans were 200 times faster at finding specimens and discriminating them from rocks. So on this one, humans won, robots 0. But that was in 2000. The fight is not over yet. I did ask Ms. Gross about the possibility of using drones for searching. And the big problem is batteries operating at temperatures that are usually high temperatures around 20 degrees. So that is the big stumbling block for is battery life for using drones to fly over and search. So still, snowmobiles is the best method. So the samples are shipped frozen to the lab in Johnson Space Center in Houston. They're thawed, characterized, cataloged. Catalogs are published twice a year, and anyone who has a legitimate need for them can request samples and for doing research on. They want to know what you're doing with them, and they want all the pieces back in the end if you cut them or things like that. But to date, they have collected over 22,000 specimens, and that is a number from 2015, according to their website. They haven't updated it since then. And they've collected over 85% of the world's cataloged meteorites in Antarctica. So more information on ANSMET can be found at Case Western University's website here. And NASA has the curator's website here. And that has information about all their meteorites. You can look at the catalogs that they published there. And so next we're going to go from things going down to things going up. The long duration balloon flights in McMurdo. They don't actually fly out of McMurdo. They have air base where they drag a whole bunch of equipment out to and fly it out of there. So they In the summer, there's something called a circumpolar vortex that's fired up by the continuous daylight and the katabatic winds. So this is a typical flight path for one of the balloons that are released at McMurdo. They follow the polar vortex around and around and around. A good flight is going around once, a great flight is going around twice, a super flight is going around 3 times. Occasionally, the vortex is very complex. Sometimes it'll take the balloons out to sea and they'll be lost at sea and they won't get their equipment back, but that doesn't happen too often. So flights can last from hours up to a record 55 days. Initially, all data was stored on board because there was no real way to transmit data on the continent. All of them need to be terminated before winter sets in so the payload can be recovered. And given the fact that all the priority is given to moving personnel, not equipment, that's sometimes a bit difficult. They'll often fly in, remove the hard drives and so they can get the data and start analyzing it, but they'll have to leave the instrumentation on the ice until spring. Lately, though, they've redirected satellite resources. Forget the string of satellites they're using, but they also use Iridium satellites as well to increasingly download data in real time off of the balloons when satellites are available or flying overhead. They need naturally circumpolar satellites to do that. Now, their launch windows is a month long, and when the launch window begins depends a lot on when the polar vortex starts going. So, and the end of the window is determined by the seasonal shutdown requirements, when flights are available to get their equipment in and out, etc. So, since all flights into the interior cease after February 15th, all equipment needs to be retrieved before then. Now, it takes 9 to 15 days to make one complete loop around the continent. And ideally, they want to terminate near McMurdo after 1, 2, or 3 circuits. As I mentioned earlier, a few payloads have been lost at sea. There was one payload that was due to make a 4th loop back, but it wandered outside the polar vortex and actually reversed direction and headed farther out to sea, unfortunately. But it happens. Now, the satellite Cream completed 3 complete laps around in 42 days between December 15th and January 27th of 2005. That was a nice, outstanding one. So you can see it was launched here. The red is the first loop around, and then it goes to this pale green for the second loop around the continent. And then the 4th loop is this blue line here. And I bet they were biting nails when it was over open water here, but they terminated right here and were able to recover on land. Now the record was 55 days. I forget the year. It was probably, I think, 2008 or so, Super Tiger. That did 3 complete loops around as well, but they were slightly slower. I used to have an animation of this going around so you could see the path as it goes, but I don't know what happened to it, and none of the websites have it anymore. Now, many, many balloon launches have been launched from Williams Field and outside of McMurdo. All of them have nice acronyms. As I said last month, you can't get funded unless you have a cool acronym. So they all kind of, sorry, what was that? Someone have a question?
I think someone just snickered, that's all.
Oh, okay. So they've done probably closer to 180 balloon launches now. They sometimes do 3, 4 in the season. Sometimes they can sneak in 10. A lot depends how the polar vortex is behaving and the actual launch requirements of the specific instruments. But all launches follow the same basic format. They have to prepare the instrument on site. They have to inflate the balloon, deploy it, and then monitor it in flight. Now, recently published in 2021 was a paper where they analyzed 40 successful balloon launches over a 10-year period. And all of these colored tracks are, the circular patterns. They were analyzing the polar vortex to try to do some understanding. They were correlating altitude versus location versus time of launch, trying to get a better understanding on what the polar vortex is doing at different times of the season and how possibly to better predict the best windows to launch certain instruments. Now, this is the instrument BLAST being loaded into the payload assembly building at Williams Field. This is initially how it arrived on site in pieces, got hooked up to the crane, and then they're going to open these doors and drag everything inside. And this is during final assembly when most everything is assembled and it's almost ready for launch here.
Is that optical? I don't think so. Infrared.
So this is a different instrument hanging on the vehicle launch vehicle. So basically, they'll have the balloon tethered to the top of here and draped across this guide and laid out all the way across the ground off site, off to the side. And then as the balloon goes up and over and stand vertically, they'll drive this out of the way and release, and the payload will start rising with the balloon. So here you can see the launch vehicle with the instrument boomerang hanging off it. So the balloon is 800 feet long. These trucks over here are all filled with helium to fill up the balloons. And here's all the tethering systems, and then the balloon actually starts about over here. Now, it doesn't look like much in there, but when it gets up to altitude, it all fills up the whole volume of the bag due to the lower pressure at altitude. So they go up to 26 miles at cruising altitude. And here's one that was just launched. Here's that launch vehicle. It pulled away right before deployment, and here is the payload right here going up with the balloon. So the actual material of the balloon goes to about here. So all of that will inflate into a big bag like this when it reaches altitude. It takes about 2 hours to reach cruising altitude, but they come down a little bit faster once you cut the cords and they start descending by parachute at the end of their run. Now, this is the payload after a safe landing. Naturally, they're coming down at speed with a parachute, so you never know what's going to happen when you find them. But everything has to be taken apart into small pieces to fit in the small twin otters or helicopters to get everything back out of there. Now, let's talk about one of the specific instruments. A lot of them go up for a lot of different reasons, studying different parts of the electromagnetic spectrum. But this one is a sub-millimeter telescope, built a little differently than that one we talked about in the South Pole, Astro. But this one is not off axis. This one is built with an obstruction. So this is actually the primary mirror around here, and you have a secondary here, and all these foil things are shields to keep stray electromagnetic waves out of the optical path. So here's a CAD view of it. So you have solar panels down here that are helping to power the instrument, and on the back side, and all the instrumentation is here. And this can actually swivel up and down to change elevation, and the whole pivot system here can rotate the whole thing around 360 degrees while it's hanging to view it point at different parts of the sky. So this is a side schematic view labeled. Those two tubes that are coming out over the top over the primary are star cameras, so it can tell what it's looking at and where it's pointing at, and has a GPS antenna to help with location too. So you have your primary here, your secondary in front of it, and this is the range and elevation it can look at between 25 and 60 degrees. And you have your reaction wheel, which helps with spinning it. And this is a emperor penguin for size.
Jim, can you hear me?
Yes.
Mario has a question.
Sure, ask away, Mario.
How long an exposure can it do on a balloon?
And how does it stay steady like that? Gyroscopes?
Well, when it's cruising at altitude, I don't think there's much wind disturbance because it's such a low pressure. But I don't really know about exposure terms. I didn't get that far into it. Yeah, actually, I've never really heard them mention exposure times really on any of these like submillimeter and microwave instruments. But this is the basic optical path of the instrument. Here's the primary mirror you saw, the secondary mirror. So it's a basic Cassegrain system going through a hole in the primary. And this bit back here is what's enlarged over here. This is all submerged in liquid helium at sub-Kelvin temperatures to keep the detector planes cold. So you have a mirror over here and a spherical mirror over here. And this M4 mirror is, for some reason, a Leostop with a calibrating light in the middle of it. Why you need a Leostop, I didn't really figure out, but they needed it in their design. What's not shown, this is the focal plane for the 500 micron detectors, but there's a pair of dichroic mirrors in the path here which deflect the signal for the 250 micron and 350 micron signal out of this plane towards different focal planes of detectors. That'll show up better in the next set of slides. But BLAST saw several iterations. The original BLAST flew for 12 days in 2006, collected a lot of data. And the second version, they updated the detectors and they added polarization abilities to it and increased the number of pixels. And that they flew for 10 days in 2010 and again for another 16 days in 2012. Now, the most recent iteration, BLAST TNG, the next generation, that launched in 2020 and is actually the last balloon launch in Antarctica I have on record. I don't know if the website didn't monitor any after that or if that was just due to COVID restrictions. But behind the primary mirror, here's the little window where the signal comes in. And here's that strange little W-shaped optical path. And the whole thing is submerged in the bath of liquid helium with all the refrigeration units around it in this big insulated cryostat. So these two are the dichroic mirrors, which will deflect the signal to two different detectors that are coming towards, actually going away from us in the optical path. So this is a upside down version of the previous slide. Here's the optical window coming in, goes back to here's your first spherical mirror, and then it goes to that M4, that Leostop mirror, which they picture up here. Then back to this other spherical mirror, and it goes through these two dichroic mirrors that deflect the path of the 250 micron signal and the 300 micron signal, and the 500 micron detectors are mounted on this this piece of aluminum right here. This is the full assembly covered up, flipped upside down, I believe. So you have the inline focal plane here. The FPA is focal plane assembly. So that's your 500 micron one, and your 250 micron one is here, and your 350 micron one is here. So the beams get deflected sideways to the various detectors here. So it can read in all three wavelengths simultaneously. And these are the different detector arrays at each location. So naturally, you can fit more detectors on a 250 micron array than a 500 micron array because of the size you need to detect the particular wavelength. Now, this is an interesting new detector technology they're using on here, in that every single pixel on here has a different resonant frequency. So it's kind of like self-multiplexing. So they can read out the different resonant frequencies to determine which pixel they're looking at instead of having complicated multiplexing electronics afterwards. Now, earlier generations used traditional bolometers as their elements. Now, I'm wondering what the fourth generation South Pole telescope detectors are going to use, if they're going to use some form of this MKIDS detection system, or if they're going to stick with transition edge sensor bolometers. Now, their mission was to detect submillimeter polarized interstellar dust that's flowing around magnetic fields in the galactic center. Some of that was actually mapped out by that instrument Astro at the South Pole years earlier. But it's going to be the first polarimeter with the sensitivity and resolution to go on small scale features that they say are critical to understanding the origin of structures in the interstellar medium. Now, that's in the best possible world. BLAST TNG, the next generation, was designed for a 28-day mission. Now, what happened, unfortunately, it did not fulfill its mission and crash landed after 20 hours aloft. During launch, a carbon fiber separator strut was damaged and critically failed after 16 hours of being under strain aloft, and it disabled the telescope steering system, so they made the decision to bring it down. Now, how do you bring down a mission? This is the inside of a C-130 plane. They have a special palletized console that goes inside there. They fly up to within line of sight of the balloon, and then they trigger the release that drops the payload off of the balloon. And then they have to witness it hit the ground, and then they trigger another release that releases the parachute from the instrument, so they don't drag the instrument along the ground, damaging the payload. That was the old way, but recently they developed this automated system for parachute release that would automatically release the parachute when it hits the ground, so they don't quite have to go through all of that anymore. So now they do it remotely from a NASA facility in Texas, I believe. But your payload is on the ground. What do you do with it then? Everything has to break down and fit inside one of these Twin Otter small planes or inside a helicopter. So this is the instrument that they're bringing down in the previous photo. I forget its name. It's not BLAST, but these are all the components of it, a little sled they had to drag stuff towards the airplane. Now, the current launch facility has been in use since 2005. It's the third facility since 1992. They had some structural failures over the years and improvements. They have like radar domes over here, fuel facility, helium storage somewhere off site right here. But these two buildings are where they do the pre-assembly for the instrumentation. All 6 buildings are on skis, and since they're a little bit of a distance from McMurdo, they drag them all back to McMurdo for overwintering to keep them safe. Now, winter's approaching, and it's time to put away their toys. So here they are, dragging one of these payload buildings back on skis. So they have to keep the skis on heaters just to break them free from the ice. Otherwise, they wouldn't be able to move them. So they got to sort of liquefy a little layer there, make it a little more slippery. So at 80,000 tons, they're the largest movable structures in Antarctica. So for more information on stratosphere ballooning, this website, StratoCat, it's not affiliated with any science program, but they have information on every stratosphere balloon launch program in the world, basically, whether it's from the Northern Hemisphere, from McMurdo. Basically, they have information on all the sites with great links to all the different launches, information about all the instrumentation, or links to the actual websites that govern the instruments. And it's a really interesting website. So thank you very much. I'd like to thank the following: the National Science Foundation, whose brilliant work funds the best science in the world, Bartol Institute, who got all the science and astronomy and the Antarctica kicking, University of Chicago, whose 2016 job listing for South Pole Machinist got me interested in what goes on there in the first place, my friend Bill Jeffers, who was inspiring me to apply for the job, but I came to my senses, and my wife Sue for putting up with me while I was doing this, and all the members of my home club, Amateur Astronomers Incorporated, and the Gloucester Area Astronomy Club, for all your enthusiasm and support. And now I guess I'll open up for questions.
Thank you very much first.
Sorry.
Bill, I'm going to stop your sharing so I can see your handsome face.
There you go.
Right. Anybody on the line have a question for Jim?
Yeah, you mentioned that one of these types of balloons was taken down by this large transport aircraft. I'm assuming the other balloons are deflated and brought down by some other means, maybe serendipitous or accidental. What determines the length of the flights, and how would you normally expect to deflate the balloon?
Well, normally the payload is cut free from the balloon and falls via parachute. The balloons are not deflated. And prior to the development of that automated parachute release system, so the payload wouldn't be dragged, all of the flight terminations were done via the C-130 and that command system you saw in the picture. I forget the rest of your question.
That's just about it, because I know nothing about this, and I was wondering what the difference would be, because you said some of them were brought down by the aircraft, and it begged the question, how are the rest of them brought down if they're not brought down by this aircraft?
Yeah, that was the original method. So they did it all by line of sight.
And what would roughly be the correlation between the theorizing or collection of something about interstellar dust and the cosmic rays or neutrons that you're actually studying? Does someone have a theory about the connection between those two?
Well, that telescope was looking at sub-millimeter band radiation at 250, 350, and 500 microns. It wasn't looking at cosmic rays. There have been other balloon experiments that looked at cosmic rays. They've looked at microwaves. They've looked at all kinds of wavelengths of electromagnetic radiation that the Earth's atmosphere is opaque to.
So what is the relationship between the neutrons you're studying and whatever theory there is about interstellar dust?
Well, I don't really have an answer for your question, because
Okay.
that instrument wasn't looking at neutrons.
Ah, okay, thank you.
It was looking at sub-millimeter frequency light. As far as durations of the flights, when they want to bring them down, a lot of it depended on if the instruments were having problems. They used to bring them down anywhere they could after they came back over the ocean. Unfortunately, sometimes they're at high elevations. So they made the decision to bring them down at low elevations at as close to McMurdo as possible, so they wouldn't have to go too far in the field to retrieve them, one, and so that the workers who are retrieving them and disassembling them wouldn't have to be working at too high altitudes, straining themselves in the process, because there were definite health risks involved.
So you're never in a position where you got like one of those big trucks like they show launching the balloon anywhere near where the balloon comes down. So everybody ends up disassembling the whole thing.
It's usually dozens to hundreds of kilometers from McMurdo where they fall.
Yow.
Yeah. So
Nothing easy about this job.
What's that?
Nothing easy about this job.
Oh, no. Nothing's easy down there. But what's funny is they have balloon launch facilities up in northern Canada as well, but they say the logistics of getting things to the South Pole is so well coordinated that it's cheaper to do the balloon launches from McMurdo than to move everything up to the northern Canadian locations. Go figure.
Jim, I think there's a question for you in the chat. Can you find that?
Yes, a lot of the balloons end up in the ocean. The question was, do some balloons end up in the ocean? Yes, quite a few of them have. Yeah, if you go to that StratoCAD website, it'll if you go to the McMurdo site, it'll give you the disposition of all the balloons that were coming down and what happened to them. And if it landed in the ocean, it was non-recoverable, it'll tell you that.
Cool. Any questions in the room?
International collaboration? Is there?
Yes, the instrumentations come from a wide range of institutes all around the world. But the launches are conducted all by the U.S. Antarctic program.
Great, thank you. And another question here?
Thanks. First time here at Rama, it was great. Thank you so much, Dr. Knott. My question is about why the missions are terminated. Is it because they completed the mission, or like what makes the decision that the balloon is come now?
Well, all flights into the Antarctic interior out of McMurdo terminate on February 15th. So if you have a certain time window where the instrumentation can fly, and once you get out of a certain season as well, the polar vortex dies. So they start meandering off in odd directions. They did try leaving a few balloons fly extended periods of time just to see what happens to them in the off season and kept tracking them. But they had no intention of actually recovering those. But yeah, if you want to recover them, you have to bring them down like a couple of weeks before February 15th, or they're going to be out in the field all winter.
If the balloon is lost, is the data lost as well? Isn't there can it not be like a local satellite, like have a transmission locally? The data is not lost in case of balloon.
I can only make out half of your question, but I believe it's about data. So all the data is stored on hard drives on board the instruments, but in the last 10 years or so, they've been allowed to have more bandwidth on satellites that are passing over. So they've been able to download data in real time if the polar orbiting satellites are overhead that they have permission to use. Now that's not available for all instruments, but it's more and more data is downloaded that way, but everything is stored on board on hard drives as a backup, and they have to go into the field to at least retrieve the hard drives, even if they leave the rest of the instrument in the field till next spring.
Shout it out, Bill.
All right, fascinating talk. The meteorite collection is fascinating. It just goes on because of that conveyor belt.
Yeah.
Bringing new meteorites to light. But the ballooning program it might be taking off in the near term, because the Stratospheric Observatory for Infrared Astronomy is about to be decommissioned, SOFIA. And so there will be a need for, if not orbital, suborbital or balloon investigations. And towards those ends, I know that University of Massachusetts Lowell has a program led by Supriya Chakrabarty with a telescope which I think operates in the ultraviolet, for heaven's sakes, on a mount that NASA has now provided that can actually do all the pointing. I was wondering whether you've been able to learn a little bit about that.
No, I haven't heard of that project, but there have been threats to defund SOFIA just about on every funding round, and it's always managed to get funded somehow. It's at least 10 times I can think of, there have been threats that SOFIA was going to be gone forever. So don't expect it to go away that fast, but don't quote me on that.
Might be good for taking bets.
I believe SOFIA operates in the infrared as well. That's why it has to fly at altitude.
Mid and far infrared, correct. And a little submillimeter. So it might be an expansive time for the ballooning program.
Oh, it's never stopped. Well, except Some, like 2020 was the last launch when the last, the next generation went up. But yeah, sad way to end it, 20-hour flight, but there'll be others.
Right.
How the polar vortex season has been affected by climate change?
He froze. Oh, he did.
I'm sorry, could you repeat that a little louder?
Do you know if the polar vortex season has been affected by climate change?
I am not 100% certain. That might be part of what they're looking into with that recent study with all the balloon position data over time over the last 10 years. But I think more the glacial breakup has been more of an issue than the polar vortex, because the polar vortex is solar driven.
Hey, Jim, what altitude are these balloons flying? And did they ever consider flying it like a kite with a tether?
26 miles, you'd need an awful long kite string.
Yeah, I guess. Carbon fiber works pretty good nowadays, though.
Still has weight.
Yeah, you can have balloons holding it up.
Yeah.
All right, I think there's one more question in the chat there, Jim, and we'll call it a day.
I think it's a pun. Says, did you mean an expansive time for ballooning? Are you saying that the quantity of ballooning is ballooning?
Yeah.
You just wanted me to read that, I know.
All right. Thank you, Jim. Really appreciate it.
Been my pleasure, my pleasure.
Thank you so much.
Thank you. I really enjoyed it.
Thank you.
And I hope to see everybody online on September 9th. We've got a great program planned, and the guy should be healthy by then.
Thank you, Michael.
Thank you, Mike.
Thanks, Mike. Thanks, Jim.
Thank you, Michael.
Good to
Thank
see
you
all
very
of you
much.
guys.
And
Have a
Norton
great
has
weekend.
the best science nobody
you.
ever hears about.
Yeah,
I'm hip.
thank you all.
Good day.
All right, bye.